Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. An essential linear algebra topic that is frequently used in machine learning and data science is matrix factorization, including singular value decomposition or SVD. Although learning SVD from a linear algebra textbook may seem to be too abstract, SVD forms the foundation of data compression and recommendation systems that are at the heart of huge companies like YouTube, Google, Amazon, and Netflix. Therefore, in this video, we discuss the main ideas behind singular value decomposition and answer questions like what is SVD, how does it work, and what are SVD's applications. In the second part of this video, we will have a step-by-step implementation in Python using Google Colab, which means that you can replicate these experiments without even installing Python on your own machine. Before we get started, if you are not subscribed, please consider joining the team. Also, please do me a favor and leave me a comment down below so I can interact with you and better understand what topics to cover in the future. Let's consider a matrix of size m by n, which we call here A. If you're familiar with numpy, A is also called a two-dimensional array because we have two axes, one for the rows and the other one for columns. With the singular value decomposition or SVD, we decompose the matrix A into three other matrices U, S, and V. Hence, A can be written as the product of U times S times V transpose. Just as a reminder, the transpose of a matrix simply means that the rows and columns get swapped. So to summarize, we assume that A has m rows and n columns. And in this decomposition, we see that U has m rows and columns. S has m rows and n columns. And the matrix V has n rows and columns. This means that both matrices U and V are square matrices, and S is rectangular. Now explain these three matrices individually to understand their properties. The columns of the matrix U are called the left singular vectors, and the matrix U is orthogonal, which means that the inverse of matrix U, U inverse, is equal to transpose of U, which we show here by U transpose. This is a really useful property because we know that finding matrix inversion is difficult in general, and in this special case, we can simply transpose the matrix to find its inverse. Now let's take a look at the matrix V. The columns of V, which they correspond to the rows of the matrix V transpose, as we color coded here, are called the right singular vectors. And V is also an orthogonal matrix, which means that the inverse of matrix V is equal to its transpose. So in that sense, matrix V is very much similar to U that we saw in the previous slide. In my opinion, the most interesting and important part of computing SVD, or singular value decomposition, is to analyze the matrix S in the middle. The diagonal entries of S are called singular values, and all remaining entries, all the off-diagonal elements, are all zeros. Here we call the diagonal elements S1 and S2, and one thing that is extremely important to remember is that we sort these singular values in non-increasing order. So this means that S1 is greater than or equal to S2, and similarly if we have more singular values. So they are sorted in non-increasing order. So the bigger one is first one, and then we have the smaller singular values. So in order to compute SVD in NumPy, where we use for computing with arrays, there is this module called linalg for linear algebra, and we can use linalg.svd. And the first input argument is the input array that we have, and mostly we work with two-dimensional arrays, like the one we saw, the matrix A, and that means that we have to give that matrix A to this built-in function. And the way that it works is summarized in the documentation page. So this function gives us the matrix U and also the matrix V. And then the only thing that is very important here to remember is that because the matrix S that we talked about it in the previous slide is always diagonal, meaning that all the elements on the main diagonal are these singular values and all the off diagonal elements are zeros, we can simply just store the diagonal elements as a one-dimensional array. And then whenever you want to construct this matrix S in this form that we have, in this two-dimensional form, then you can use np.diag. So np.diag takes a one-dimensional array and puts those elements on the main diagonal, and then we will have zero padding in all other entries of this matrix. So if you're interested, you can go to this page and see more about singular value decomposition in NumPy, but I summarized the main points here. And another important option that we have here is this thing that's called full underscore matrices, that by default is true, and we can set this also to be false. So the difference is that if you look at this matrix S here, the third row, we have 0 and 0, which means that there is nothing really useful in that row of this matrix. So we can just simply have a 2 by 2 matrix where S1 and S2 are on the main diagonal of this matrix. So in this case, we can get rid of the third row, and similarly, we can get rid of the third column of the matrix U. And that happens when you set full matrices to be false. So then the matrices U and V are not necessarily square matrices. So that's like the only difference here. But it can save us a lot of memory and storage space, because then we are gonna just keep fewer columns and rows in these matrices. So now let's look at this example. We import numpy as np, and we also import svd from numpy.linalg. And by the way, as I promised at the beginning of this video, we will have a full implementation of this at the end of these lecture notes. So here we create a matrix A that has 3 rows and 2 columns. And you can call the function svd, and we set the option full matrices to be true. So this will give us square matrices U and V, because it's set to be true. And now we can print U, which contains left singular vectors, and then the diagonal matrix S. And remember that the S that this function gives us is always a one-dimensional array, which you can see here that the first element is 1.62, and then the second element is 1. And as we said, these things are always in non-increasing order, meaning that the second one here, if you look at it, is 1, which is less than 1.62. And then for showing the right singular vectors, because it is common to have these singular vectors in columns rather than rows, that's why I transpose that matrix that I call VT, because by default this VT, these singular vectors, the right singular vectors are in the rows. And then if you want to have these in columns, you can just call the transpose, and now we can have them in the right format. But this really depends on the notation. So some textbooks, for example, they have row vectors. Some textbooks, they have column vectors. And it is more common to have these left and right singular vectors in columns rather than rows. So now, using those right and left singular vectors and singular values, we can try to reconstruct the original matrix. So in order to do that, I take that one-dimensional array S, and I create a two-dimensional array using this process that we create a matrix full of zeros of size 3 by 2. And then we put the elements of S, which if you remember, there were 1.62 and 1 on the main diagonal. And now we have to multiply these three matrices, right? U and this matrix S in a two-dimensional format, and then VT, which contains the right singular vectors. And in order to do so, we can use again another useful built-in function available from numpy.linalg, which is called multi_dot. So in this case, you put in one list all the functions that you're trying to, all the matrices that you're trying to multiply together in the right order. So we are multiplying U, S, and V transpose, so you can see that here. And if we do so and compare this with the matrix A, we see that they're actually very close. So the first element is 1 to the power of 10 to the power of 0. That's that E0. And then we see that we have that negative 0.8. And then we have this e to the power of negative 18, which, numerically speaking, that's, 0 in terms of like the actual importance of that location. And then similarly for that 10 to the power of negative 16. And if we want to be a little bit more precise, what we can do, we can use the norm function from, again, linalg, and try to find the difference between matrix A and its reconstruction using this singular value decomposition. And here we use something called Frobenius norm, which after we subtract these two matrices element-wise, we are going to square all those elements, add them together, and then take the square root. Which, as we can see, is something in the order of 10 to the power of negative 16. And for us, this is equivalent to 0. So the other question that we have, what is the application of SVD? Why is it so important? So let's go back to that example that we had originally. We have matrix A, and then we have its singular value decomposition. So we have the matrix U that has 3 columns, U1, U2, U3. And then we have the singular values S1 and S2. And then we have the right singular vectors that we have them in the rows of the matrix V. So now using simple linear algebra operations, we can show that we can write this matrix A as the first singular value, which is S1. And remember, S1 is just a scalar, it's a single number, so it's very easy to multiply. And then we have the multiplication of the first column, and then the first row, which is V1 transpose. So this is something that we call this a rank 1 matrix, because if you're familiar, this is something that's called like outer product, right? So you have 2 vectors, and then one of them here, for example, is n by 1, and the other one is 1 by n. So when you multiply, you get something which is n by n. But it's a rank 1 matrix because of this special structure. And then here in this case, we have also the second singular value, the second column of U, and then the second row of V. And as we talk about it, because here if you look at it, the third row of the matrix S, we have all zeros. So this means that the last column of U doesn't really do anything here in terms of representing the matrix A. And if you want to go a little bit more in detail, that's something that we say that this matrix is rank 2 because we only have S1 and S2, means that we have two non-zero singular values, and this would be a rank 2 matrix. And the reason that this type of decomposition is very useful is that let's say you have done this singular value decomposition and you see that S1, the first singular value, is much greater than S2. So this means that the first term has is much more important than the second term. So if you need to reduce the redundancy in data or reduce the size of data, you can get rid of the second term and just approximate the matrix A using the first term, which is S1 U1 times V1 transpose. And that's what something that we call it low rank approximation, which is very, very useful. And in recommendation systems, when you have huge matrices where let's say each row corresponds to different users and each column refers to different items, there is definitely some kind of structure or correlation in this matrix. And this means that if you do singular value decomposition, you will have this type of decaying singular values that you can get rid of some of them, and this will allow you to extract more information from incomplete observations. Because what happens is that when you have a lot of items, a lot of users, for example, you can ask all users to rate all items in your database. So you need to be able to make predictions about the missing sort of like ratings. And that's sort of like the basic idea here, that you can use this type of low rank approximation. And here what I've done to explain low rank approximation, I've created this matrix A, which has 5 rows and 3 columns. And we import SVD. And here what I'm doing is that I'm setting these full underscore matrices to be false. So if you look at the shape or the sort of like the size of each of these singular vectors and singular values, you can see that matrix U is 5 by 3, so it's not anymore a square. And then the S is a one-dimensional array with 3 elements. You can also see the values of those 3 elements. And then the matrix V transpose, which is, we call it here VT, is also 3 by 3. And here is exactly what we were talking about. That if you look at it, S1, which is the first element of this one-dimensional array S, is much greater than the rest, because the rest of them are like 10 to the power of negative 17. So this means that we can just keep the first one and get rid of the other 2 singular values. And we can do so using this very simple technique that we have these matrices U and V transpose, and we decide that the rank is 1 here, because if we look at it, we only had 1 dominant or major singular value. And so because indexing starts from 0 in Python and NumPy, we are gonna start from 0 to 1, and 1 is excluding, so we are gonna just pick the first column of U, which is indexed at 0, and similarly the first row of V transpose, and also the first element in that one-dimensional array for singular values. And then we can just multiply all these matrices together. Instead of using that multi-dot function, here I'm using np.dot. So this is just when you want to multiply 2 matrices. That's why I'm gonna first multiply U and S, and then I multiply the result of this by V. And when we do this multiplication, now we have this approximate version. That's why I call it a low rank. And we can again find the difference between the original matrix A and A low rank. And we can see this is in the order of 10 to the power of negative 16, which again, this is almost 0. So this means that we have a perfect reconstruction of matrix A using this very simple formula that we have one singular value, one column vector times one row vector. So you can see that now, instead of saving all those 5 by 3, which would be 15 elements in the matrix A, we can just save all these entries for U1 and V1. So we have 5 elements in U1, 3 elements in V1, and also one singular value. So we have some type of data compression. So that's for the lecture part of this video. And then we're gonna have a step-by-step implementation in Google Cloud. See you soon. Okay, now let's have a step-by-step implementation of this in Python using Google Cloud. As we discussed before, the first thing you need to do is that you need to go to Google Drive, drive.google.com, and then create new. And if you have already created a Google Cloud file, we can find it here. Otherwise, you use Connect More Apps. So here we use the Google Collaboratory or Google Cloud. And the first thing you want to do, you can change the name of your Jupyter notebook. We call this Dr. Data Science for obvious reasons. And then you start with importing modules that you want. So here we're gonna start with importing numpy. And also because we're using singular value decomposition from numpy.linalg, we are gonna import SVD. So now we run this cell, and now we can create the two-dimensional array that we had in the lecture. So we use np.array, and now we give a list of the rows that we have. So the first row was 1 and negative 0.8. The second row was 0 and 1. And then the third row is 1 and 0. So if I run this, we see that we get an error message, which is basically saying that NP is not defined, and that's because we didn't use import numpy as NP. I use this because I want to show you that how easy it is to get these error messages, but the good thing about Python in general is that it's usually easy to find out the main cause of the problem. So here we're going to import numpy as NP, and the other one for SVD looks good. So now we run this, and this time we don't have any error message. So now we can use print A, and we can see that now we have this two-dimensional array. We can also use .shape to find the number of rows and columns. So obviously here we have 3 rows and 2 columns. Now, in order to find the singular value decomposition, we use U, S, and then V transpose. That's the notation that we had, but I just call this VT. So this doesn't transpose the matrix V. This is just the name, so that I remember that this is the transpose of V, not the V itself. And now we use SVD. The first option is to give the two-dimensional array that we have. And that's what I like about using Google Cloud. So you can see that here, all the instructions that we had in the documentation page. So let's say put full matrices equal to true. So this is the default option. And if I do so, now I can look at the shape of these singular vectors and singular values. So U contains the left singular vectors, and then S has the singular values, and VT has right singular vectors. And if we print this, we see that U is 3 by 3, 3 rows and 3 columns, and then the variable S is a one-dimensional array with 2 elements. So you can see here the difference between a two-dimensional array and a one-dimensional array. When you have two-dimensional array, you have two numbers. So you have a tuple, for example, like 3, 3. But when you have a one-dimensional array, you have 2, comma, and then there's nothing there. So that means that S is a one-dimensional array. And then we have this matrix VT, which is 2 by 2, which is a square. Now we can write the same thing, but this time I'm going to set full matrices to be false. And we can just copy paste the previous line to see the difference in terms of the number of rows and columns. As we discussed in the lecture, because now the variable S has only 2 elements, so this means that the last column of U is not useful. So that's why when you set full matrices to be false, now we automatically get rid of that column. So now the matrix U is 3 by 2, and S is a one-dimensional array with 2 elements, and VT is also 2 by 2. And now we can also look at the elements that we have here. We have U, we have S, that's our one-dimensional array. And then if we want to have the right singular vectors in columns, we can use dot transpose, that I can use this option, or you can use np dot transpose. And this sort of like summarizes the main steps that you have to take to find the singular value decomposition. It's relatively straightforward. You need just from numpy.linalg import svd. And then the very important option here is that whether this full underscore matrices is true or false. And if it's false, then the nice thing is that you're gonna save a little bit of a space for cases like this that you have rectangular matrices. The matrix X, the matrix A here is rectangular. I want to thank you for watching this video, and please don't forget to like and subscribe.